Okay, cool. Yeah,
There we go.
that works. Okay.
Great. Yeah. So, Brandon, please take it away.
Yeah. Hi, everyone. So I guess I have like the worst position for talks because I'm after John and then I'm also right before lunch. But hopefully you guys will be able to follow some of this. And I guess what I'll be talking about is our work in the Lucan group, working on photonic interfaces for neutral atom quantum processors, which I guess Ziv covered a bit as well as John. So some of the motivation will be redundant, but that's okay. So I guess the things that we work on are these neutral atom array processors where we're able to project optical tweezers into vacuum to trap hundreds to thousands of neutral atoms. Then we're able to excite them to Rydberg states to be able to do 2-qubit operations. And we can encode the quantum information on these really long-lived hyperfine qubits, which then gives us really long coherence times. So it is like kind of a nice system. And for the past, I'd say like decade now, things have been really progressing very quickly, where now the 2-qubit gates are high fidelity. And using this, there have even been demonstrations of logical operations with this like new kind of zoned architecture. And then also scaling up in like the last couple of weeks, 2 papers have been accepted to Nature where people have shown system sizes of 6,100 coherent qubits, which is extremely exciting from Caltech. And then also continuous operation of 3,000 qubits where we're able to continue to reload single atoms into optical tweezers while continuously running for like hours. I guess 2 hours is what they say. But then at some point, we think that these systems will eventually reach a limit of how many qubits you can have. And so people are starting to think about ways of interconnecting modules. And most of these proposals, which there's been like almost 10 probably coming out over the last few years, always mention having optical cavities to enhance this collection efficiency and increase your interconnection rate. And there's even some companies that are starting to work on this, like NanoQT, which also they have some ideas on how to do this, but this is becoming a more and more important problem as the Rydberg atom arrays kind of reach these like scaling limits of how many qubits you can have in a single system. And so that's really the focus of my research, which is trying to find like an optimal cavity. And I guess we've already, I guess since it's a cavity community, we already kind of know there's just 3 numbers that really matter in a way, which is kappa, G, and gamma. And so what kind of cavity do I want? I want a cavity with a high cooperativity, of course, to get this collection efficiency out. And then I also want high outcoupling efficiency because the thing that matters is really not like fully the cooperativity. You also have to get these photons out. So you want to also make this input mirror a lot more lossy than the total loss rate of the cavity, which means that the photons don't get scattered into free space. You get them into the mode that you want. And then lastly, I'm interested in something with high bandwidth so we can really pump out these photons pretty quickly. One thing that I've been trying to like introduce to people, and I hope this is, I think this is the right community to start to spread this, is a new definition of cooperativity, which I think is also in John's paper on this small waist cavity, which is defining like the highest possible cooperativity you can ever achieve with a given cavity that's only limited by the scattering rate. So if I really make this mirror like as reflective as I can till I'm just limited by scattering losses, that will set this, this maximum possible cooperativity, which I call C intrinsic. I think people call it C internal as well. But then that is what you can then plug into this collection efficiency equation, which has the C over C plus 1 per cell enhancement, as well as the total leakage out, this like ratio of leakage in this mirror to total leakage of the cavity itself. And if you calculate what the optimal is, then you get an efficiency maximum that's given by this equation. So the thing that really matters is actually for a given cavity, calculating this parameter and seeing if you get a good enough collection efficiency, and that kind of sets the fundamental limit. So high cooperativity with our new definition and high bandwidth. And then the other things that are interesting and important is being able to actually put atoms inside. So if your cavity is too small that you can't fit your tweezers inside, that kind of limits your capabilities. And then also, as John was saying, Rydberg compatibility. So finding ways of, like these small cavities I really like, but they are pretty close to the surfaces. And I guess people here know that that's kind of a problem. But I think there's ways around this, which I'll talk about. So the outline of my talk is talking about 4 cavities that I've worked on throughout my PhD, which is first these 1D photonic crystal cavities, then fiber cavities, which are fantastic. And I got to meet Jakob Reichel, which is very cool. And then since then, we've also created some other versions of these cavities, which are kind of interesting that I'll talk about later. And then Misha had me also include some physics, as he said in the fiber cavity section. So I'll make it quick, it'll be fine. Yeah, to some, I mean, I would consider cavities physics, but it depends who you ask, I guess. So the first type of cavity is the 1D photonic crystal cavity. So I guess Chen-Lung mentioned the ring resonators. This is a different type of nanophotonic cavity where you can take a waveguide and pattern it with holes, which effectively act as Bragg mirrors and confine the mode volume to these extremely small volumes. So these cavities can essentially get you the highest cooperativity you can really imagine. So if you were to be inside this mode, you have something like a C of 40,000. But unfortunately, when we trap our atoms on it, we can only get evanescent coupling, which results in a slightly lower cooperativity. The other nice thing about these interfaces is we can taper a fiber down and collect photons directly out of the mode, which makes it kind of nice. On top of that, the bandwidth it's like a gigahertz line width, so we can really extract photons extremely quickly. The other nice thing is it's extremely small. We can put it in a vacuum chamber like this, so it's compatible. It's also so small that we hope that the stray electric fields are relatively small, and we've measured some of these things, and we can see that we would in principle be able to do high fidelity Rydberg operations. So then when we measure this cavity by putting an atom on the top, we can get our cavity QED parameters, and we see that we can get a C of 70 with these really high G's and kappas. But the problem is we only get this cooperativity occasionally because of the thermal sampling of the atom. So we have this exponential fall off in the electric field. And then due to the atom motion, we actually sample a pretty wide variety of cooperativities, sometimes even 0, which is a little bit of a bummer. And that is kind of unfortunate in terms of the atom integration. And then with this platform, we've demonstrated things like coherent transport on and off of the device, where we can make entangled states on the cavity and then drag them into free space. We've also demonstrated this Rydberg excitation near the cavity, which shows that Rydberg compatibility is like feasible. And one of the main things that kind of was my takeaway early on in my PhD was the main problem is this coherent transport onto the device. The transport's actually fairly lossy unless you do it like very adiabatically, which means that it's going to be slow. And if you're trying to use this as a networking interface, that's really going to be the bottleneck on your rates. So if I were to like kind of grade this cavity, I'd give it a B in cooperativity. Like, and the sampling is kind of an issue. It's an S tier bandwidth. And then atom integration, the transport's really kind of a problem. And then Rydberg compatibility, it could be better, but we can probably deal with it with other methods on the atom side. So then most of my PhD was kind of like pushing this one out of the chamber.
Grades or
I honestly, I mean, C of 70 and getting a B, that's like, yeah, it's and yeah, I guess S, it could be, yeah. So fiber cavities, most of my PhD was pushing out the nanophotonic cavity and then putting in the fiber cavity. I like fiber cavities. You can talk to Jakob Reichel here more about fiber cavities. I've probably said Jakob Reichel like way too many times during my PhD because I always say, see Jakob Reichel. But the nice thing about these cavities is so I mean, we all know what fiber cavities are. You take a fiber, you cleave it, you CO2 ablate it, and then you coat it with HR coating. This gives you a really high finesse optical cavity on the tip of a fiber, which means that it's also very small, so we can actually sneak our tweezers in and we can have a pretty big optical access. The way that we design our devices, we essentially just glue shear piezos onto a glass slide and then a glass monolithic mount onto the top of that, and then we can put the cavities in and glue them down, and then they'll be stable and able to modulate and lock. We can put it directly in a glass cell, and then we just we put the device inside the vacuum, and then we just slide our vacuum chamber into our optics, and then we're able to run experiments where we're able to make a MOT right above the fiber cavity, trap atoms, and then drag them into the cavity mode. So the way that our experiment runs is we have the 780 mode, which we use for all the quantum things where we resonantly scatter light off of the rubidium. We also have 810 mode for locking, and then we add an additional 850 mode for trapping, which then has this incommensurate wavelength with 780, but we can get around. So the first thing we do is we measure the cavity. This is like the better measurement. Then we spoil the finesse by throwing an atom inside, and we can measure G as well. And this gives us a cooperativity of around 100, with basically no thermal sampling now, so it solves that issue. We can consistently just see a cooperativity of 100. And when we park our laser on resonance, we can then do things like state readout, where we can then measure the state of the qubit, whether it's in the f equals 2 manifold or f equals 1 manifold, and we do this relatively quickly, so like 10 microseconds compared to this like 5 millisecond number for free space with a relatively high fidelity. The other kind of neat feature that we'll use later to do some physics, I guess is what it's called, is we can also do error detection. So rubidium has many different states. We have the 2 qubit states, which we use these magnetically insensitive states. And we can actually read out the difference between these qubit states and these other states by just performing multiple readouts with rotations in between. So with min-circuit rotations as well as readout, we can do things like one readout, and then we can detect whether it's in one of these states. Then we can apply a pi pulse, which rotates just the qubit state, and then we can read out again. And then the unique combination of these will tell us if we were in the state 1, 0, or in this error state. And so then error detection we can use for other things. So now that we have this, we can then try to map out the mode. And what we do to kind of tell us where to place the atom is we scan the tweezer across the mode, and we drop it at different places and look at the avoided crossing. So then once we see where the avoided crossing is biggest, we just put our atom with the high C zones, and then we can operate with 2 atoms. So 1 atom coupled to the cavity, you get a G splitting. Once you put a second atom inside, you get this √2 enhancement, where it's like a simple Hamiltonian, but you get another atom coupled to the cavity, and you get this √2 enhancement in your splitting. We can look at this as a function of cavity detuning and probe detuning, which just looks pretty. It's the like textbook avoided crossing. And we can think about what these states actually correspond to. If we look at them in terms of energy, these are like the bright and dark states. So these are addressed states of like 1 atom excitation, 1 photon excitation. And with 2 atoms, it's the same thing, but now it's a shared excitation between the 2 atoms. But we know from the Hamiltonian that there should be an additional state, which is this dark state. So it's like a 0 energy state. That's 1 atom excited out of phase with the other, but we don't see this here. And it's because we coupled to just the cavity component by driving the cavity. But now if we were to drive from the side, which we can now do with the fiber cavity instead of the nanophotonic cavity, we see this nice like middle peak show up, which is kind of cool. And then if you just take a cross section and look at it, it's kind of like a blockade. It's like an anti-blockade. It's like a conditional resonance dependent upon if you have 1 or 2 atoms in the cavity. So then we thought, oh, it's like a Rydberg. But then you think more and you're like, wait, I mean, we're in the cavity community. We know that the error rate you get for any deterministic gate in like a cavity system will always have an error rate scaling as 1/√C. So that's kind of a problem because even with a C of 100, this is not very good. And in the past, we know that we've been able to do things like Herald to increase this fidelity. So this is something we did with the nanophotonic device, where by performing detection, we're able to create higher fidelity entangled states than this 1/√C. But then you have to detect a photon, and with like collection efficiencies being low because we're not very good at fiber coupling, then we have to think of other methods. So one thing we can do is actually use some of these proposals where you Herald on atomic states, where you use the other states of the atom, these like error states that we can now detect to correct or detect when you have errors in your gate. And so this was quite promising. So then we started looking into how to do this with our system using not just like these proposals, but also like this blockade mechanism we kind of saw. And it turns out there is a way where you can pick the right atomic states, and I'll kind of go briefly over this, but basically you can rewrite this basis into a basis like this, where now qubit states will have the resonance that's now dependent, or you'll have a qubit state dependent resonance, where now certain qubit states will couple up to this dark state, while other qubit states will have no coupling or like some blockade in a way. So we can use this to do things like carving out pieces of a wave function. And if we pick the right states in rubidium, we can actually make the errors fairly detectable, and this can also be improved in the future. But for this, we just use these states. So now what we can do is we can prepare different qubit states and look at how they interact with this drive. So if we prepare the 1,0 state, it couples directly to the dark state and it decays very quickly. While if we're in the 1,1 state, the decay is suppressed due to this avoided crossing. So we can essentially pull out parts of the wave function, this like 1,0 state, without affecting the other state. So the first thing we do is something that's cavity carving. If you detect photons is the name of it. We prepare a superposition of all qubit states, then we carve out one part of the wave function, then a pi pulse to carve out the other part of the wave function, And by doing this, we're able to end with an entangled state. Depending upon how long we do this pulse that carves out parts of the wave function, we get more and more entanglement until it starts to drop off due to other effects within the atom. And we can prepare entangled states with some fidelity around like 91% with a success rate of 30%, now higher than other methods where you're detecting photons because you can now detect atomic states. The other thing we can do is more like the Rydberg blockade method, like these like pi 2 pi pi gates, where you go up and around and acquire a pi phase shift while the other state does not, giving you a phase gate. So we can prepare different states of the qubit and look at this phase shift that we acquire depending upon what state the control atom is in. And we can see this pi phase shift. Then we can embed this in a circuit and measure what the fidelity of that is. And we get something like 76%, which is, it's cool, but it's not like quantum computing. But I think these things do have some like, there could be like some promise in the future, because essentially what you're doing is creating a gate that succeeds with a probability of 1 minus 1 over root c with a fidelity that's now in principle close to unity, but it's all detectable errors. So if you were to embed these gates inside some of these like erasure biased codes, I think there is like an interesting future there, but not one that I'm going to be exploring. And so just to sum up the fiber cavity physics part, we did some gates. Okay. And then since then, we've been upgrading the experiment. So this has been mostly Danilo building up atom arrays to be coupled to the cavity. So we made multiple upgrades where before we were basically trapping our atoms right here, which is a lot harder than trapping them way up here. So we can trap atom arrays now and then move them in and out of the cavity. We can see the atoms. Uh-oh. Oh, yeah. Okay. And you can see the cavity because it's small, which is maybe not preferred. And then we can see as the atoms transit through the cavity, we get avoided crossings, which is nice. And we can even do things like drive-by readout, where we see the dip in photons every time an atom crosses the cavity, which we can then use to do some kind of like state readout while it's moving, which is kind of nice because it gets around some of this movement problem where normally the time that's like the bulk of movement is the speed up or the slow down. If you don't have to slow down to do things like atom photon entanglement or readout, this could help things quite a bit. Okay. And so now the grading scale for fiber cavity. I really like fiber cavities, but like it gets an A for cooperativity, A for bandwidth, B for atom integration. It did take us like quite some time to figure out this Mott thing, but transport's a lot better than the nanophotonic cavity. And then for Rydberg compatibility, we spent some time trying to do things like sputter gold onto the fiber cavity to get rid of like straight charging effects, but this was always fairly hard because it's the tip of a fiber and not like a wafer or a chip. So that kind of motivated us to explore different directions. So what do we want to change about the fiber cavity? So this is a slide from before. Fiber cavities are really nice. Here's like an updated slide. Fiber cavity tips are about 125 microns in diameter, but the only part you use for the mirror is actually this like middle, maybe 40 microns. So we could actually cut this down quite a bit, giving us a little bit more optical access. So we could use smaller cavities or have more atoms. Laser ablation seems to give this like limit of 2 angstrom, which is a really good surface roughness, but it can definitely be better. And then that would increase this C intrinsic value. And then the mirrors are also kind of Gaussian shaped, which for longer cavities, it becomes challenging to maintain high finesse. So if you were to have a perfectly spherical mirror, you can see that your cooperativity enhances up to this like concentric regime where you can still have a stable cavity. And you can also work with longer cavities, which is nice. But for fiber cavities, people typically set this like clipping loss number, which is kind of arbitrary depending upon which cavity you're working with, but your finesse will normally fall off, sometimes even before the confocal regime. So we want to fix the shaping. And then the other thing we can do is if we can make these longer cavities, we can make it so that one mirror focuses onto the fiber core, which gives us better collection efficiency. So when you think about a fiber cavity and the fiber coupling directly into the mode, you think about this like fiber mode coming out, it just sprays out. And the overlap of that with the cavity mode is what gives you kind of this collection efficiency, this like mode matching, where if you emit a photon into the cavity, how much gets into the fiber. And this number falls off really quickly with length if you have like a curved configuration. But if you could do something where with a more flat fiber cavity plus a more curved other mirror, then you can maintain these really high efficiencies for collection. And then reducing surface roughness, we can maybe try to get that better. See Jakob Reichel, I think maybe he's figured out a way of making this better as well. And then the other thing that could be nice is if we can do more fabrication on these things, because there is like some developed understanding of like charge noise reduction for things like the nanophotonics community, which maybe we can leverage. And so there are known methods, and this method is from the Trupke group in Vienna, where what they do is a double isotropic etch. So they take silicon, they coat the whole wafer with resist, and they poke a hole in the resist, and then they isotropic etch once, then they remove resist and isotropic etch again, forming something that's basically perfectly spherical. And then by doing some additional smoothing of silicon, where you oxidize the surface and etch away the oxygen layer or oxide layer over and over again, you can get down to roughnesses on the order of 0.5 angstrom. So then I talked to some people I know in the Lonkar group, which is Sophie, and Sophie was able to take this method and she said, oh, that's like kind of easy to do in the clean room. And then within a week, she was able to replicate it and make it a little bit better, which is kind of crazy. But then we were able to measure these things and see that it's basically a perfect sphere, which is what we wanted. And then if we measure the surface roughness, we can see we get like 1.52 picometer or 152 picometer, which is 1.5 angstrom, which is like a fiber cavity. But it turns out this was not precise enough, so we went to AFM and we could measure something like 0.5 angstrom. So these are like pretty good cavities once they're coated. This is pre-coating. But then we can send these off for coating from 5.9. Thank you, 5.9. And we can make these very large arrays of micro mirrors, and we can also cut them into arbitrary shapes using Bosch etching, which is a very developed technique in silicon to make structures that have very little like clipping for the tweezers. So we can make even smaller structures. And we can make arbitrary structures, which can also be nice and flexible. And on top of that, now that we have something kind of wafer, like chip-like, we can put it in a machine that can maybe sputter gold on top, or there's some of these like conductive dielectrics, and maybe we can start to explore this for some more Rydberg compatibility. Then we started functionalizing these devices where we can take these cutouts and then we just use the same fiber cavity design, but drop the fiber cavity and glued a micromirror on the other side, where we can now make a fiber cavity silicon micromirror hybrid device. And we can also do things at both telecom and 780, where we can get even higher operativities. And we also get to see things like I mean, one of the things that really sold it for me was I was measuring and I was like, man, I have this really weird Fano effect. Like I can't get rid of it. And I realized I was seeing ring down on like a cavity that's like 100 microns long. And that's when I was like, these things are pretty good, pretty narrow. So then in terms of future directions with this, we've built a second experiment. So this is an effort led by Andre. So if you have questions about it, Andre has a lot of answers. And so we started building it about 2 years ago. And then I think within a month, we had single atoms in the experiment. And then I guess this was about 2 weeks ago, where we put the new device inside the chamber and then are now trying to get atoms inside the cavity after a brief bake out period where we now can see, we can now see atoms trapping kind of near the cavity, which you can see scattering here, and atoms loading in and out. And if you have questions about this, there's also a lot of other really interesting science going on here, which, okay, the clicking is not, yeah, a lot of really other interesting scientific directions that Andre's been kind of like figuring out. And it's very cool. You should see Andre's poster, but there's a lot of extra additional like new stuff that's been going on with how to do these things where we want to try to extract telecom photons directly out of rubidium. And then for the other experiment, I guess 1.0, it's now going to be upgrading to 3.0, where we're changing the device a bit, where we're making use of these silicon micromirror technologies where we get more optical access as well as tapered fiber cavities to get better, higher finesses as well as longer cavities. And then we should be able to get more atoms inside with longer cavity lengths. Unfortunately, our fiber cavity should look like this, but it looks more like this. where the core is not where the ablation is, so our collection efficiency actually suffers from that. For the silicon micromirrors, I'd rate it S for high cooperativity. If you calculate the C intrinsic, it is like the highest you can measure, or you can calculate for any of the cavities that we think about. It's high bandwidth. Atom integration, I'd say about the same as fiber cavity. And then Rydberg compatibility, I think with these fabrication methods you can do, it does kind of make things a little bit better or more promising. So a C. Now, while doing that, we also kind of stumbled upon some other way of making mirrors, which is kind of funny. I guess this is like kind of the crazy one in a way. So this is what a sample looked like that I was trying to measure, where here you can see here you can see this like micro mirror array here. And I was asking the fabbers if they could, I was asking Sophie if she could like just clear out the back so I could measure transmission, because the signal to noise is so much better. So then she tried to do it. She tried to etch behind here, but she ended up just making this thing that I started to call the swampy sample, because it kind of looks like a swamp. And you can see this HR coding line ends here, but there's still HR coding suspended above these holes. And if you look at them very carefully, you can see that they're like kind of buckling. So if you look at an angle, you can see the bending of the light. And so if I just shine a laser on that, you get like a 300K finesse cavity. And that's without even trying. So then Sophie tried to do this on purpose in the clean room, where all we have to do is polish a silicon wafer, send it to 5.9, who coats it. And also, yeah, 5.9, I kept asking if they could get better and better, like lower and lower transmission coatings, but they kept saying 10 parts per million. And then I was like, we really want like better. And they were like, oh, we thought you wanted photons out. So they kept giving me coatings that were more high transmission than they can possibly do. Eventually we fixed that, and then we get to these higher finesses. But once we get the coating from 5.9, we can flip over the wafer and then poke these holes into the back. Then suspending the membrane, suspending the coating, and then due to the strain from the IBS coating, the shape buckles, forming something that we can use as a cavity. We can then make these in arrays. We can also cut them out into really small shapes and then form cavities using these. We see that it's almost perfectly symmetric in the X and Y direction. And we also have a pretty good understanding of what the buckling mechanism is and what kind of shapes we can get to. And using that, we can just change the hole diameter on the input to change the radius of curvature. We can get things between, we've made smaller ones now of like 900 micron ROC, and I think we can get lower, but it's an open question, up to radius of curvatures of around 20 millimeters. Then we can make cavities out of these mirrors and measure them. The way we measure length is by looking at the mode structure. So we know the radius of curvature very well, and then we can calculate what the length of the cavity is using this mode spacing. And then the way that we measure kappa is by looking at swept ring down. So by just scanning a cavity really quickly across a laser that's a fixed frequency, we see some of the light still circulates and interferes with some of the other transmitted light through the cavity, resulting in this really kind of pretty thing that we can fit analytically. Then for different radius of curvatures of the cavity and different lengths, we can look at how the finesse changes as a function of length. Due to this weird shape, it does fall off at certain lengths, but for short lengths, we can see a relatively flat finesse on the order of like 800 to 900,000, and then fall off once we get to these longer lengths. And this is not just one sample. We can really make these arrays and just kind of press them up against each other, and we can see finesses that are always pretty much above 300,000, okay, 200,000. But I think with like proper cleaning, these things will always pretty much outperform 300K finesse. The other thing we can do is just basically glue them directly to each other to make these micro cavities. So we can make really small cavities where this has a line width of about 1 megahertz, and this one would have a line width of about 200 kilohertz. And with 200K finesse, we can really make these like compact high quality factor resonators. The other nice thing about these is we have this wafer that we can just break off pieces from, and then we can Bosch etch arbitrary structures. So we've been making mostly circles, but you can also imagine making handles so that it's a lot easier to structure these things. And then with these like smaller sizes, we can also have a lot less clipping loss for atom experiments. And so then we've started to think about how to integrate these with atom experiments, where alignment's also a lot easier, so we can make these bigger structures that maybe don't need to be as stable because we're in the confocal regime. And then we can also put things like box piezo's, which should maybe help with electric fields. And on top of that, we can do all of the same fabrication techniques we would think about doing with the silicon micromirrors. And I also want to stress these things are like really small. They basically look like small tubes, and picking them up with tweezers, there's like a 50% chance you'll just shatter it instantly. It's also while working with it, if you get your face too close and you breathe too hard, it's gone. But yeah, we can make bigger ones with handles next time. So for buckled micromirror cavities, they're not as high cooperativity because they're bigger. They're a little bit lower bandwidth because they're bigger, but in terms of sizes, now that you can get to these like millimeter sizes, so maybe that's better for Rydberg. And then also with the shielding things that we can do in the clean room, maybe that also helps a lot. Okay, so overall score sheet. I think that these are pretty prohibitive. I think if the fab stuff works, it makes these a lot better, but it is like, I mean, it's an open question. Everyone's looking for like what the best photonic interface for neutral atoms is. I really like the small cavities because I like to see that avoided crossing, but that's a bias that I should probably get over. But these buckled mirrors are pretty interesting. Okay, and then, so 1D photonic crystal cavity, I think that this like transport is kind of a deal breaker, and thermal sampling is also a problem. Fiber cavities, it's been the bulk of my PhD. I really like it. Thank you, Jakob Reichel. And then the silicon micromirrors, I think, are an improvement over fiber cavity, and I think combining them is also a pretty interesting direction because you can hit these really high collection efficiencies. And then I think these buckled mirrors are just interesting. I think the fabrication is interesting because it's very scalable, and I also think this intermediate length regime is something that's kind of special because you really can't get these like diamond milled mirrors at ROCs below like 5 millimeters maybe, and these kind of can fill that gap. So you can get something like a super polished mirror that can go between like 5 millimeter and 10 millimeter to get these concentric cavities, and fiber cavities kind of fill this other region. And with this new fabrication, these new fabrication methods, we kind of fill the gap in between. So it offers a few more geometries. And they're not super crazy cavities because it's all 1D, but yeah, maybe the buckled one's like crazy. So now if we look back at these numbers, another kind of interesting thing I think about is like, what is like the parameter space that each of these cavities is in? And maybe this is like kind of useful to the community, which is we really like to work with these really high cooperativity, high bandwidth cavities. And another thing to note is you can always increase your bandwidth and sacrifice this cooperativity intrinsic by going up this line. So things like fiber cavities and buckled cavities, they can even be pretty high bandwidth. These are cavities where I assume you can hit like a finesse of 1 million if you get really good coding and really good alignment. I don't know how realistic that is. And then I've also thrown up the high NA cavity with the, like, they have this paper in prep that I hear that has better parameters than their previous paper. But in principle, this is also very interesting because of the high bandwidth and the reasonable cooperativities. And another thing I think about is like scale wise. So if we think about how big these silicon micromirror arrays are, they're relatively small, which means that if we have a 1.5 millimeter field of view, we have plenty of space to do atom operations. And maybe this makes me a little bit less scared of the charging because of the small size. And then buckled microcavities are in this other regime where you still have this optical access on the side where you can maybe send Rydberg beams and share a B field with a B field along the cavity, which is nice. But then once you go to concentric, you kind of cut out this optical axis part. And if you go even bigger, you start to cut even more. And so that's kind of the takeaway for me is that I really like microcavities. I think they're scalable. It's also really easy to stabilize them. It requires a lot less alignment. And once they're in vacuum, they basically don't shift. So I think it is in that way something I could make maybe 10 of in order to make multiple networking units. The only problems that need to be addressed further is things like Rydberg integration. And that's something we're actively working on. Then I'd like to thank the team. So this is an earlier team that worked on mostly the nanophotonic devices. And since then, we did these fiber cavity works with this team. And then Andre joined and has really taken off on like functionalizing these silicon micromirror devices. Again, see Andre for answers to your questions. And then this is the team of our collaborators that worked on the buckled mirrors as well as the silicon micromirrors. And now our team's expanded more where we're thinking about other cavity geometries and going beyond.
Questions for Brandon?
For the dark state cavity emission, we rely on like you first accept dark state and do the minutes that no longer symmetric.
Yeah, no, you point out something that's hidden. But so the dark state's supposed to be dark. It shouldn't have photons coming out. But what essentially happens is if you are to drive into the dark state, that also means you can go up to the second excitation manifold of the Tavis-Cummings model, where it's like some superposition of like EG, GE, and GG with 2 photons. And then that's how we get photons out. So we just drive harder and then we can see this third peak. So it is like kind of wrong to say that we're seeing the dark state. We're going through the dark state and then seeing a different state.
Yeah, good stuff, Brian. Can you comment on the mechanical stability of the buckles on the cavities?
Yeah.
If you breathe too hard, you lose it. But if you found it again,
Yeah, it's actually fine. A lot of the samples measured for the paper even are like we dropped them in the clean room. There was one day where Sophie was fabbing them and then she like called me and she was like, can you come to the clean room now? And then we spent like an hour picking up mirrors off of the ground. But they're very like stable. I think we lost like quite a few. Like just because we couldn't find them. Oh, I think pretty much all of them that we found. Yeah. Yeah, but this was also with the bigger diameter. With the smaller ones, if I picked it up with the tweezer, 50% chance I crush it. Yeah, it's gone.
How, if you were going to try to make an array of mirrors that were all the same depth, which technique would you use, and how identical would the depth be?
Yeah, that's a good question. I guess one thing we're interested in is making like arrays of micro mirrors. We haven't really measured because I guess we need, so if we use things like PL, so it's like optical measurements of depth, I don't really trust the sensitivity you need is better than what the sensitivity. Yeah, so yeah, we have to make a cavity of like all of them and we haven't done that yet. But I'd say it's probably better than a nanometer, but not as good as like we'd probably have to do some kind of individual tuning if we want to stabilize all of our high finesse. Yeah, so we want to try thermally tuning, but we haven't done that yet.
Great talk. In the vacuum cavity, do you see any optomechanics effects from the membrane?
Yeah, so we can measure acoustic resonances on it just with interferometer. I think for some of these, they can be as high as like a megahertz for the smaller ones, but then go down to like 100 kilohertz. It is kind of interesting because there's also these like LIGO experiments. Actually, like funny side story, but the buckled cavities, we looked for if other people did this, and it turns out that like Simon Groblocker during his PhD was making these, like he had silicon wafer HR coated, then he'd make cantilevers out of the HR coating to make optomechanical cavities. And so it's a very similar idea. And this is actually the track that led to this like Aspelmeyer low Brownian noise mirror coating, because he saw that the cantilever's quality factor was limited by the intrinsic material loss, which is also Brownian noise because of like fluctuation dissipation. That's kind of a sidetrack, but yeah, we've measured the acoustic resonances.
Because limit your cavity performance if you ignore it.
We've been able to stabilize it to like narrower than the line width, so I think we're okay.
On one side, we show you how less probability.
Yeah.
Is that just because
The
coding packets?
Yeah, the finesse there. But yeah, if you go up in lambda, you get this finesse enhancement because cooperativity has like a hidden lambda in it, which kind of almost cancels out, but then comes back. But yeah, like the telecom, we do benefit from the line or the wavelength being longer. So cooperativity gets better.
That's helpful. I'm curious, like there are a few people there, especially like for the application you want to do.
So I think we want to just optimize total collection efficiency. So we'll find a really high intrinsic cooperativity cavity, then reel back on the finesse to get photons out. And also the nice thing about having high C intrinsic is it makes this regime where it's like good collection a lot wider. So we can reel back even more and then just be comfortably always collecting probably greater than 90% of the photons. But yeah, I think that's kind of the regime we're going for.
One more.
You went to the regime where you're around millimeter, like, or as close as you can with all these three devices. Which one can give you the highest NA or area?
So I think the silicon micromirror is like the best. It's just something we have to develop more because we can't get light out the back. I think eventually we'll improve the fabrication to combine silicon cavity and buckled cavity and make a buckled silicon microcavity where we can collect light out. The main reason is this thing is perfectly spherical. Like we could make a concentric microcavity probably, but yeah, I think that would be the best. All right, with that, I think there's already a line for me for lunch. So let's thank all the speakers again.